Imagine you have a virtual robot, maybe a little humanoid model, and you drop it into this huge twisting maze.
Yeah.
Your job is to teach it how to solve that maze, how to find goals, how to just move. But here's the catch.
That's the catch.
You can't give it any instructions, no rewards, no good job, not even a hint when it gets close. It has to learn everything from scratch.
That sounds, that sounds almost impossible. For years, reinforcement learning, or RL, has completely depended on that feedback, on rewards.
Exactly.
Without them, how does it even know what a good move is?
Well, that's what our mission is for this deep dive. We're looking at a method called contrastive RL, or CRL. It's a self-supervised thing. But the real story isn't the algorithm. Not really.
Oh.
It's what happened when they realized the problem wasn't the code. It was the size of the AI's brain.
And this is the part that, really stands out from the sources. The thinking for so long in RL was that you had to use shallow networks. We're talking 2, maybe 5 layers deep.
Right, keep it simple.
But these researchers just threw that idea out. They scaled the depth up to an incredible 124 layers. And the result wasn't just a little better.
It was a transformation.
A total transformation. We saw these acrobatic leaps in what the agents could do.
So, unprecedented depth leading to acrobatic superpowers. That's the headline. Okay, let's unpack this and find out what these deep brain agents can do that the shallow ones couldn't even dream of. Okay. So let's set the stage first. What kind of environments are these agents actually in?
They're facing a whole suite of tasks. Some are basic, like just locomotion learning to balance and walk. Others are way more complex, like an ant model navigating a really tricky maze.
And there's manipulation stuff too, right? Pushing objects.
Exactly. And the setup is what they call an unsupervised goal condition setting. Meaning the agent has to figure out how to get from where it is now to any other place it's told to go. It has to discover the physics, the layout of the world all by itself. No rewards from a human.
Which brings us back to that old problem. Why was everyone so sure that deep networks were a bad idea for this kind of RL? Why the shallow brains?
It really came down to an instability problem. In these big environments, especially the mazes, any kind of reward is, it's incredibly sparse.
Sparse how?
The agent could take thousands of actions before it does anything that gives it useful feedback.
It's like a chef trying to invent a new dish, but the only feedback they get is someone saying, tastes good or tastes bad an entire year later.
That is a perfect analogy. And when you have a huge network, hundreds of layers deep, and you only get this tiny, weak signal every now and then,
it just gets lost.
It gets completely lost. It vanishes as it tries to travel back through all those layers. It creates all sorts of training problems. So people stuck with shallow networks, maybe 4 layers, because they were stable. They worked, even if they weren't very powerful.
So they chose stability over what, capacity?
Pretty much. And this is where contrastive RL-CRL comes in and just changes the whole game.
Right. It's self-supervised, so it doesn't need those outside rewards.
Exactly. The agent is constantly generating its own learning signal. It learns by contrasting its own experiences.
How does that contrasting part work?
Well, think of it like the agent is grading its own homework. As it moves, it creates 2 sets of data. One is a path that actually led towards a future goal it picked for itself.
A successful attempt.
And the other is just a random, irrelevant path. The network's job is just to tell them apart. It asks itself, did that move get me closer to my goal, or was I just wandering?
So by just classifying its own actions, it's building its own internal map, like a little GPS of what works and what doesn't.
Precisely. It learns to recognize what a successful move feels like without a human ever telling it. And what's so cool is that scaling networks has been the big story in language models.
Yeah, models with hundreds of layers.
And in computer vision, too, RL was always the exception. So these researchers thought, well, what if CRL is the key? What if it stabilizes training enough that we can finally scale the depth and see if we get that same kind of jump? Which brings us right to the experiment itself. They took their CRL algorithm, which already worked well, and they started making the networks deeper.
Starting from the standard 4 layers?
Yep. They went from 4 to 8 to 16, 32, 64.
Yeah.
And then they just kept going. All the way up to 256 and 34 layers.
So did they hit that instability wall everyone was worried about?
Not at all. It was the complete opposite. They found that with CRL, more depth led to these huge, sometimes exponential improvements in performance on every hard task they tried.
The numbers are pretty wild.
The scale of it is almost hard to process. I mean, on the simple manipulation tasks, performance went up by maybe 2 to 5 times, which is already good.
That's a solid win.
But then on the hard navigation, like the ant maze, it was over 20 times better. But the really jaw-dropping ones were with the humanoid. Performance there jumped by over 50 times.
And what about that one specific case, the humanoid big maze?
Ah, that's the one. That's where you really see the change. Comparing the standard 4-layer network to the 64-layer one, it wasn't just a bit better. It was a 1,051 times increase in the success rate.
Wait, say that again?
151 times.
That's not an improvement, that's a different category of existence. It's the difference between failing almost every single time and reliably solving the problem.
It's unbelievable. And it makes you wonder, is it just a smooth curve up? Or is something else happening?
And it wasn't smooth, was it?
No, not at all. This is where it gets really fascinating. The researchers saw these pronounced jumps in performance. It happened when the network crossed what they called a critical depth threshold.
So like on the ant maze, going from 4 to 6 layers didn't do much.
But jumping from 6 to 8 layers suddenly unlocked a whole new level of skill, a breakthrough. And for the really hard humanoid maze, that threshold was at 64 layers.
So it's not more layers equals a little better, it's enough layers equals a sudden flash of insight.
That's a great way to put it. The network suddenly has the capacity to understand the problem in a new way.
This also brings up a practical point. People usually talk about scaling network width, making layers fatter. Why depth? Was it more efficient?
It was, and that's a huge takeaway here. Past work did focus on width, but depth turned out to be way more effective for scaling performance, especially for something like the humanoid with all its sensor data. And, crucially, it was cheaper computationally.
Cheaper how?
A deep network, say 32 layers, might have about 2 million parameters. To get similar performance with a shallow 4-layer network, you have to make it so wide that you end up with something like 35 million parameters.
Wow, so you're getting much more intelligence for your money by going deep.
Disproportionately more. It's a much more efficient way to scale.
Okay, we've covered the numbers, which were staggering. But now for the really fun part, the superpowers. It wasn't just the success rate, it was what these agents started doing.
Yes, the change in behavior is the most amazing result. When you watch the shallow agent, the 4-layer humanoid, it's just clumsy.
What does it do?
The researchers called its policies rudimentary. It mostly just collapses. Or if it sees a goal, its best strategy is to literally throw itself in that direction.
Oh, wow.
It's just flailing.
Whoa.
It looks desperate, not coordinated at all.
All brute force, no skill.
Exactly.
Yeah.
But then, as they add more depth, something incredible happens. At just 16 layers, the humanoid agent finally learns how to walk upright.
A walking breakthrough.
A real stable, coordinated walk toward the goal. And then came the parkour.
Okay, tell me about the 256-layer humanoid in the U-maze. This is the one with the wall in the middle, right?
Yes, an obstacle, it can't just walk around.
Yeah.
And this is where that deep brain unlocks genuine problem solving. The agent developed these totally new, complex skills that were never programmed in.
What was the first one?
The first one is amazing to watch. It learned to fold forward into a leveraged position to propel itself over walls. It's essentially vaulting the barrier
It learned to do a vault.
in a single, complex, acrobatic move. But the second strategy might be even smarter. In other attempts, it learned to shift into a seated posture over the intermediary obstacle to worm its way toward the goal.
So it's adapting its body to the problem, squeezing through.
It's not just moving anymore, it's using the physics of its own body in these creative, nuanced ways. The deep understanding of its world leads to complex physical behavior.
And that deep understanding helps it generalize, too. You mentioned something called stitching.
Right, so stitching. The agents were only ever trained on short paths, goals that were like 3 feet away.
Okay.
But when they tested them on a longer path, say 6 feet, across that U-maze, the shallow networks just failed. They had no idea what to do.
And the deep ones?
The deep networks succeeded. They seamlessly stitched together the short little paths they knew into one long, successful journey.
So it learned the basic words of movement, and then its deep brain allowed it to string them together into a whole sentence to solve a problem it had never, ever seen before.
So now the question is, why did this work? Why did scaling depth work here when it failed so many times before in RL?
It wasn't just the CRL algorithm, right? There were other ingredients.
That's right. You can't just build a 1024-layer skyscraper without the right materials. They had to borrow some key architectural ideas from other fields, like computer vision.
To stabilize the whole thing, what were they?
3 main things: residual connections, layer normalization, and the switch activation function. The residual connections are probably the most important part.
Okay, explain residual connections like we're just listening in our car.
Think of a 1,000-story building. In a normal network, the information has to go up every single floor, one by one. By the time it gets to the top, the original message is garbled.
It gets lost.
A residual connection is like an express elevator. It creates a shortcut that lets the signal from floor 1 jump directly to floor 50 or floor 100.
Yeah.
It lets that essential early information travel all the way through the network without vanishing.
And that keeps the training stable even at extreme depth.
Exactly. You combine that with layer normalization, which keeps the data flow from getting too wild, and that specific swish function, and suddenly the architecture is strong enough to handle all that scale.
And with that stable architecture, what could the deep networks learn that the shallow ones just couldn't grasp? It sounds like they built a much better map.
A profoundly better map. You can see it perfectly in the ant maze. The shallow 4-layer network, its map only understood straight-line distance.
So it sees the goal is right there.
Even though there's a giant wall in the way, it thinks it's close, so it just runs into the wall over and over.
It's fooled by how it looks.
But the deep 64-layer network learned the true topology of the maze. Its internal map showed a clear, high-value path leading around the wall. It understood the actual effort required to get to the goal.
So depth doesn't just help it learn faster, it helps it understand the world more deeply. And this all works together with the data, too.
Absolutely. The researchers found that giving the models more data to practice on a larger batch size barely helped the shallow networks. But the deep networks, they unlock that benefit and use the extra data to get even better.
You need both.
You need both. A deep brain with poor data is useless, but a deep brain with lots of data to process is transformative.
And we have to circle back one last time. None of this works without one key thing.
It all comes back to the contrastive RL algorithm. They tried scaling depth with the old-school RL methods like SAC and PD3, and it was a disaster. They either flatlined at 4 layers or their performance actually got worse because of the instability. It proves that the self-supervised contrastive approach is what makes this deep scaling possible in the first place.
So if we just, pull back for a second and look at the big picture, this deep dive really confirms something important. The scaling laws we've seen in language and vision, they apply to reinforcement learning too.
They absolutely do. Scaling up the depth of a network is a fundamental building block. It directly leads to these emergent capabilities, these superpowers that you just don't get otherwise.
And it suggests that if you're designing a smart system that needs to explore and learn complex things on its own without a human holding its hand,
you have to give it a brain that's deep enough to actually represent the complexity of its world. The ability to act in a sophisticated way is tied directly to the ability to think in a deep way.
of course, we have to mention the trade-off. It takes a lot longer real-world clock time to train these massive networks.
It does. But the results speak for themselves.
So I want to leave you with one final thought, which is actually where the research paper itself ends.
They ran out of compute.
They literally ran out of compute. They only stopped at 124 layers because of the hardware they had. So if 64 layers can teach a robot to walk, and 256 layers can teach it to vault a wall.
What could 2,000 layers do? Or 10,000? What completely unexpected high-level skills are just waiting to emerge? Things like long-term planning or maybe even collaboration? What other building blocks of intelligence are just sitting there waiting for us to build a brain deep enough to find them?